Great pleasure to have Agustin Moreno here today. He will be telling us about symplectic structures from almost symplectic structures.
All right. So thanks, Lauran, for the opportunity to talk today in the Zoominar. So it's always a great pleasure to see, at least, if not familiar faces, familiar names on the screen. Today I'll talk a bit about some recent work that we've still in the process of writing up. So it's not sort of fully ready yet. But I mean, we're sufficiently confident in the results that I thought it was a good idea to already present them. So this is joint work with Fabio Gironella, Fran Presas, and Lauran Touissant. And it will basically be trying to address a fundamental sort of existence question of symplectic structures in high dimensions. Okay, so this there's a way of getting a symplectic structure out of an almost symplectic structure, and I'll try to explain exactly what we're doing in that direction. Okay, so let me start with a bit of background. So first of all, I probably don't need to remind you here in the symplectic Zoominar what a symplectic manifold is, but I will do so anyways. So you should probably know that a symplectic manifold is just an even dimensional manifold with a two form which is closed and non-degenerate. Okay, so we have this very nice sort of geometric structure which comes from mechanics. And the existence problem is basically asking, well, which manifolds are actually symplectic, right? I'm interested in trying to sort of classify things in general. In particular, I just want to ask, well, if you give me a manifold, when can I ensure that there's a symplectic structure on it? So in order to have a chance at all to be in the presence of a symplectic structure, there's always some underlying topological conditions that we need to impose. Okay? So the obvious topological obstruction to the existence of a symplectic structure is what we will call a formal symplectic structure. Okay, so this is the data of an even dimensional manifold N, which comes with a non-degenerate two form big omega, so sometimes also called an almost symplectic form. So it's not necessarily closed. And then the last piece of data is this cohomology class theta in degree 2, which is non-degenerate in the sense that if the manifold is closed, sort of its top power is non-zero. Okay, so that's what I will call a formal symplectic structure. So, the existing question basically, asks, of course, in principle, this is what you need in order to have a chance at all of having a symplectic structure. A symplectic structure induces a formal symplectic structure. The question is whether the converse also holds. Okay? So if I start with this data, can I find a symplectic structure realizing it? Okay, so this is the existence problem. And you can find that listed in McDuff Salamon's introductory book on symplectic geometry as problem 1. Okay, so this is the very first open problem, actually. So the question is, if you start with the formal symplectic manifold, does there exist a symplectic form little omega on the manifold, which is first homotopic to the almost symplectic form that you start with through almost symplectic forms, and the second condition is if it lies in the cohomology class that you fixed. So this is the existence question. Of course, you can also this is a refined version. You can also just forget about the data that you start and say, okay, does there exist some symplectic form on which I don't necessarily control the homotopy class or the cohomology class. Okay, so that will also appear in some version later in the talk. Okay? But so this is the problem that we try to address. I mean, we won't address it as it stands. I'll explain the version that we address, but this is what is the motivation. So let me mention some known facts. So this is a fundamental problem in symplectic topology. So it has been studied by different people in different ways. So there's an old theorem of Gromov in 1969. So Gromov proved using the theory of H principles that if you start with a formal symplectic structure on an open manifold, so either sort of non-compact or with boundary, then the existence problem can be fully solved, so fully understood. So yes, it can be realized by a symplectic form. Okay, I can sort of realize any homotopic class and any cohomology class as well. Okay, so this is goes back to Gromov. It's nicely explained in Eliashvili and Mishachev's book on the H principle. So, I mean, okay, the open case is sort of fully understood, but what about the closed case? So it turns out that the situation for closed manifolds is very different. So it's much more rigid. So, for example, there's a result of Taubes in the 90s. So Taubes tells you that there actually exist formal symplectic closed manifolds in dimension 4, which are not symplectic. Okay? So it's not true in general that you can realize a formal symplectic structure by an actual symplectic structure, at least in dimension 4. Okay, so this uses sort of really sort of deep geometric tools. So it uses Cyber-Witten theory, so gauge theory. I mean, the rough idea is to, for example, you take this particular case, the Taubes consider. So you take CP2, and you take the self-connected sum of CP2 k times with itself, and then you allow also to blow it up a bunch of times. And if k is at least 3 and it's odd, then this is an example of a formal symplectic closed four-manifold, which is not symplectic. Okay? So this is a concrete example to keep in mind. And sort of the way that one can prove that is using, as I said, Cyber-Witten theory. So if this were a symplectic manifold, the Cyber-Witten invariants would be non-trivial. But on the other hand, they are actually vanish because this manifold emits a metric with positive scalar curvature. So if you have that metric, there's a sort of basic estimate in Cyber-Witten theory that tells you that the only solutions to these equations are the trivial solutions. Okay? So in other words, this manifold cannot possibly be symplectic. Yeah, but those sort of the four-dimensional stories sort of really sort of hard analysis techniques in order to get this sort of result. And more recently, there's a nice theorem of Bertelson and Meignes, so 2021. So what they tell us is that in any dimension, if you start with a closed almost symplectic manifold, so this with a non-degenerate two form, then you can actually homotope it to a conformal symplectic structure. Okay, so conformal symplectic structure is, roughly speaking, the data of a non-degenerate two form such that locally, you can find locally defined functions which are positive in such that if you multiply the two form with this function, then you make your two form closed, okay? So it's some sort of a local condition. So that's why the conformal in the name. So what they tell you is that almost symplectic manifolds can in general be realized by conformal symplectic structures, but not by symplectic structures in general, like the theorem of Taubes says. Okay. So conformal symplectic structures seem to be the more sort of flexible object. But as far as I know, if you look at the actual existence problem in the symplectic categories and not the conformal one, this is wide open as soon as you're in dimension at least 6. Okay, so I'm not aware of any results in the positive or in the negative directions. Okay? So I mean, as far as I know, to my knowledge, what I will say next are the first high dimensional results. Okay. Okay, so this is sort of a bit of background, a bit of known results in this direction. So let me then move on and talk about the results. Okay, so this is what we proved recently with Fran and Lauran and Fabio. Okay, so as I sort of already advertised, we don't consider the existence problems on the nose. We consider a stabilized version of the existence problem. So it's a simple operation. We start with a formal symplectic manifold, and I will say that its stabilization is, well, I take the product with T2 of my manifold and I stabilize all the associated data. So I just take, in the obvious way, I just take an area form on T2 and then just sum it to the cohomology class, and then also to the two form omega. Okay, so I mean, you might complain here because stabilization in the literature means different things. So some people call stabilization and take the product with C, a reliable domain, or maybe S2. I mean, for the purposes of this talk and also the paper, I will call stabilization taking the product with T2. Okay. So I'm trying to define myself with future sort of questions. Anyways, but so this is a stabilization of the formal symplectic manifold, and then we will ask the existence problem for this type of stabilized formal symplectic structure. So the stabilized existence problem is, when can the stabilization of a formal symplectic manifold be realized by a symplectic form in the same sense as before? So where I fix this this two form and I fix this cohomology class. Right, so that's a question that we will be interested in addressing. In order to state the main theorem, I need a definition. And this is the notion of a positive symplectic divisor. Okay. So a positive symplectic divisor in a formal symplectic manifold will be a codimension 2 closed-up manifold sigma, satisfying 3 different assumptions. First of all, up to homotopy of the two form amongst almost symplectic structures. I want to assume that the restriction to the divisor is actually symplectic. So it's closed and non-degenerate along the divisor. The second condition that I want to impose is that the Poincare dual of the divisor, which is now a two-form, is exactly coincides with the two-form that I start with. So theta in my formal symplectic structure. And then the last condition, and this is the positivity condition on the normal bundle of the divisor. So I want to assume that the normal bundle is positive in the sense that its first term class is represented by the cohomology class of this two-form restricted to the divisor. So now, because I'm assuming by the first point that this is symplectic, in particular, it's closed. So it gives me a well-defined cohomology class, and I want this sort of compatibility condition. Okay, so this is what we consider a positive symplectic divisor. So one sort of word of warning, sort of, for example, if you take a blow up, you don't get a positive symplectic divisor. Right? You get a negative one in general. So self-intersection is negative. So for example, in dimension 4, positive symplectic divisors is just like surfaces which are which the two form is sort of symplectic and such that they have positive self-intersection. Okay, so this is a notion, and then the main theorem is the following. So it says that, well, if you start with a formal symplectic manifold and you assume that it emits a positive symplectic divisor, then the theorem says that its stabilization can actually be realized by a symplectic form. Okay? So we can control the cohomology class, and we can also control the homotopy class, okay? Under this sort of compatibility assumptions on the device. So in other words, if I can solve the problem in codimension 2, so if I can make my sort of two-form symplectic along some codimension 2 submanifold, then we're claiming that you can also do that, but after you take the product with T2. Okay? So that's a statement. And one thing that's sort of important to recall here is that there's a well-known result of Donaldson from the 90s using sort of almost holomorphic techniques, that up to scaling of a symplectic form, if you start with a symplectic manifold, then you can always find positive symplectic divisors. Right? So in some sense, the assumption, if you're trying to find a symplectic structure, the assumption on the existence of such a divisor is a natural condition. Okay, and it's not true that the converse holds. So there are examples of formal symplectic manifolds with symplectic divisors, but which are not symplectic. Okay? So this is exactly, for example, the example by Taubes that I mentioned before. Okay, so that guy has divisors, but it's not symplectic. Okay, so it's a necessary but not sufficient condition. Okay. So that's the statement of the theorem. So the goal of my talk today will be to explain what goes into the proof of this theorem. Okay, so at least give the main ideas and the techniques that we use. Okay, but any questions on the statement? Okay, so then I'll move on. So, but let me mention a corollary of this theorem, which I think is one of the most interesting results in dimension in low dimensions, so in dimension 4. So if you start with a closed 4-dimensional manifold, then we can say things about the stabilization. So the first point in the corollary is if you assume that this closed manifold is simply connected and formal symplectic, then its product with T2 actually admits a symplectic structure. Okay, some symplectic structure. Okay, so I'm not sort of claiming anything about being able to control homotopy classes or cohomology class. Okay, I'm just saying there exists some symplectic structure on the product. And the same thing if I assume that it's almost symplectic and it satisfies sort of this topological condition, which is fairly mild. I mean, in the sense that that's positive and negative second betti numbers are at least 2, so both of them. So just remember, it's just the dimensions of the maximal subspaces in which the intersection form is positive definite or negative definite. Okay? So this sort of appear all over the place when you do gauge theory. Right? So under this condition, and you can say, well, most four-manifolds satisfy this condition. So we're sort of throwing away. I mean, the ones that we're throwing away are the minority in some sense. Then the product with T2 is actually also symplectic. So these are the corollaries, and in particular, if you consider the example that the Taubes studied, so this sort of blow up of connected sums of CP2, as I said before, this is formal symplectic, but not symplectic, but it's simply connected. So the first point tells you that when you take the product with T2, it actually is symplectic. Okay, so in other words, the obstruction they had before for finding a symplectic structure vanishes when you take the product with T2, which is a bit sort of very unintuitive, at least to me. So I don't know. So some funny phenomena happening here. Okay, so that's the corollary for four-dimensional things. So in some sense, it follows from the main theorem, because what we end up doing is finding divisors. Okay? So what we do is, well, all of the manifolds in dimension 4 that satisfy the conditions actually have positive symplectic divisors for some almost symplectic structure. Okay? We're not particularly claiming that if you fix any almost symplectic structure, you can find a divisor. I mean, that's a more stringent condition that we cannot at the moment sort of check. Okay, but maybe some remarks of what goes into the proof of this corollary. So I mean, this is a low-dimensional sort of statement in some sense from dimension 4 to dimension 6, but we really use sort of the heavy four-dimensional technique. So the first observation is that at least in dimension 4, formal symplecticity is purely topological. So this is an old result by Wu from the 50s that tells you that the existence of a formal symplectic structure only depends on the homeomorphism type of the manifold. Okay, so the smooth structure might change, but the fact that you have such a formal symplectic structure is independent on the smooth structure. And moreover, in 4 dimensions, the existence of symplectic divisors is also independent of, it's also only dependent on the homeomorphism type. So this follows from a result of Bohr from 2000, who studied sort of existence of pseudo-holomorphic curves in almost symplectic 4 manifolds. So that's the first observation. And then you can say, well, I can also then use Donaldson and Friedman's celebrated work in 4-dimensional topology, because this allows me to look at the intersection form. Donaldson tells me if you have a smooth structure, then the intersection form is very much restricted. It's basically diagonalizable. And Friedman tells you that, well, whenever you fix a reasonable bilinear form, then there's 2 homeomorphism types of 4 manifolds, which are topological manifolds, realizing them, at least one of them, which is not smooth at all. Okay, so Donaldson gives you restrictions. Friedman tells you, okay, there's always a world of topological manifolds realizing that, but then it allows us to sort of go case by case and discuss whether you satisfy the formal symplectic condition with a divisor, and so on and so forth. And we can do that because of the first observation, which sort of allows us to look at only homeomorphism types of 4 manifolds. And the second condition, the second sort of part of the corollary, this condition, you should really think of it as some sort of, it's actually equivalent to saying that the intersection form is strictly indefinite. Okay, so this is sort of what it really means. And we use the main result and also these results of Bohr, which tell you that holomorphic curves exist under this assumption. Then you need to make sure that they have positive self-intersection, but it's also possible to achieve. Okay, so that's in a nutshell how the 4-dimensional results follow from the main theorem. Okay, so but today I'll as I said, I'll focus on trying to explain how to prove the main theorem. Okay, so let me start then with a bunch of preliminaries. So first of all, I need to introduce the notion of an open book decomposition, and you're probably already familiar with this if you've done some contact topology. So open book decompositions on an open book decomposition on a manifold M is just a fibration defined on the complement of some codimension to submanifold B, taking values in the circle, which looks standard on some choice of color neighborhood of this submanifold B. Okay, so it's just a projection to the angle coordinate if I choose some polar coordinates on the disk, trivializing the normal directions. Okay? The notation that I will normally use is I will say that the manifold M is the open book decomposition associated to P and phi. So P is the closure of a fiber of this vibration, which is called the page of the open book. B is the boundary of all the pages. In this case, it's called the binding of the open book. And phi is here the monodromy map. So it's a diffeomorphism of the page, which is the identity at the boundary. So the picture always to remember is the one that I'm drawing here on the right-hand side. So, intuitively, I just take a book, and you should never do that if you actually care about this particular book, but you take a book, you open it up, and then you glue the front cover to the back cover using some glue. And this gluing map is exactly the monodromy. So now you destroyed your book, but you got an open book decomposition. And sort of on this color neighborhood the binding, you get this sort of picture where the pages come together radially and have the same boundary, and away from this neighborhood you get a mapping torus of some sort of diffeomorphism, this diffeomorphism phi. Okay, so that's sort of standard topological notion. Every odd-dimensional manifold which is closed can be presented in this way, so it's a very general notion, in particular in dimension 3. Okay, and they're deeply related to contact structures, okay, by the work of Giroux. Okay, I'll also explain that later. But maybe as a reminder, contact manifold, as you know, is an odd-dimensional manifold which comes with a hyperplane distribution, which is maximally non-integrable. So I want to think of it as globally given by the kernel of a 1 from alpha, satisfying this contact condition. And by work of Eliashberg and collaborators of Borman, Eliashberg, and Murphy in high dimensions, so they tell us that contact manifolds come in 2 different flavors. Okay, we have this very nice dichotomy between the rigid world and the flexible world. So if you go to the store and try to buy a contact structure, the person at the counter will ask you, okay, so what type of contact structure are you looking for? Are you looking for one which is sort of geometrically rigid or sort of geometrically interesting? So in other words, a tight one. Or are you looking for a flexible or more topological one, an over-twisted one? Okay. So the classification of over-twisted contact structure is a matter of topology, whereas tight contact structure is more matter of geometry. So usually if you hit contact structure with the pseudo-homomorphic curves, then you might get something interesting only if you were dealing with a tight contact manifold. In the over-twisted case, you always get some sort of vanishing invariance. Okay? You know, Eliashberg and then Borman, Eliashberg, Murphy proved exactly this homotopy principle, that every almost contact structure is homotopic to a unique over-twisted contact structure. So here, almost contact structure is the obvious underlying topological obstruction to the existence of a contact structure. So this is exactly the existence problem for contact manifolds in the contact category. So we're trying to address the existence problem in the symplectic category. So it's no surprise. I mean, we will actually use these results very strongly in our proof. So in some sense, it's no surprise. And in particular, sort of because contact structures induce almost contact structures, every such contact structure is homotopic to unique over-twisted contact structure through almost contact structures. Okay? So this is sort of the well-known H principle of Eliashberg and collaborators. Okay, so this will sort of appeal to these very heavily in the proof. Okay, there's also the Giroux correspondence. This is of course very, very foundational work and contact topologies. So Giroux basically tells you that studying contact manifolds is equivalent to studying open books. Okay? So contact structures in particular are supported by open books in a suitable sense. The statement is a 1-1 correspondence. Sort of contact structures up to isotopy are in correspondence with open books up to a notion of stabilization. And this is not the same notion of stabilization that I'm talking about in this talk. But, so, and as far as I know, you know, the uniqueness of this open book was open for a long time in high dimensions, but recently work of Honda in the convex hypersurface theory, now they're claiming that they can also get uniqueness in any dimension. So I think that's an interesting recent development in this theory, in particular in high dimensional contact topology. So the concrete statement is, well, you start with a contact manifold. So one of the directions of the correspondence tells you that, well, there exists an open book on this manifold and a so-called Giroux form, so the contact form alpha for the contact structure, which is compatible with the open book in the sense that the derivative of the contact form is positive or symplectic at the interior of the pages, and the restriction to the binding of the contact form is also a contact form in codimension 2. Okay, so this is sort of the concrete sort of notion, and intuitively we can think in this sort of look at this picture, and you have this sort of color neighborhood. And what you can think is that the contact structure starts horizontal, and then in the radial directions, it starts twisting in the positive direction. Okay. So that's sort of the intuition. Okay, and using Giroux correspondence is also a nice construction of Bourgeois going back to 2002. So Bourgeois tells you that if you start with an open book decomposition supporting a contact manifold, then there's a simple way to write down a contact structure on the product of the manifold with T2. Okay? And this is, you know, secretly why we consider the product with T2 and not with any other manifold. So there's also a Bourgeois construction for other surfaces. So it's conceivable that our results also apply for other types of stabilizations. So we just haven't thought about it yet. Okay, so I'll just consider only products with T2. Okay, so this is a fairly simple and straightforward construction. using the Giroux correspondence. So the construction is you start with the Giroux form, you take coordinates Q1 and Q2 on the two torus, and you consider what's called a defining map for the open book. So the open book, you want to present it as phi divided by its norm, where phi is a map from the manifold to R2, which has two components, phi1 and phi2. Every open book can be described in this way. So if you start with this data, then you write down this sort of one from here, you take alpha plus this linear combination with the components of the defining map. And this is actually a contact form for a contact structure on the product with T2. So this is what I would call a bourgeois form on M times T2. Okay, so fairly straightforward construction. And I will denote the bourgeois manifold associated to an open book with page P and monodromy phi by BO of P phi. BO is just bourgeois of this open book. Okay. So I will also need a number of properties of this, and maybe also mention that I just saw a paper on the archive by Zhengyi, Zhou, and Russell. So they show that these bourgeois manifolds are tight in any dimension. Okay, so they're very rigid objects. So we were able to show that in dimension 5, but now they're doing that in any dimension. Okay, so I think it's also interesting property to keep in mind about this manifolds. So it's a very sort of rigid type of construction. But the observations that I will use in the proof are the following. So first of all, there's a theorem by Lisi, Marinkovic, and Niederkruger in 2019. So they tell you a very funny property of this manifolds. So they tell you that if you start with an open book and you invert the monodromy, then if you do the bourgeois construction on those, then you actually get contactomorphic manifolds. So they're isomorphic as contact manifolds. And this should be rather surprising to you, because if I do the same thing at the level of open books before taking the product with T2, this is very much not what happens, right? So if the supported contact structures, sort of if an open book supports a contact structure, but if I invert the monodromy, the corresponding contact structure in general is very different from the original one. One of them might be tight and the other one might be over twisted. So they have nothing to do with each other in principle. What this property is telling you is that when you take the product with T2, they actually become the same, which is sort of very strange. But once you sort of think about it a bit more, you realize that when you invert the monodromy, you have to invert the orientation on the manifold. And taking the product with T2 also allows you to invert the orientation back. Okay? So in principle, there's no obstruction at the level of orientations. And it turns out you can actually write down such a diffeomorphism taking one contact structure to the other. So this is what those people are doing. And there's another property of which we will use in the proof. So first of all, the bourgeois manifold depends not only on the contact structure, but also on the open book that you start with. Okay, so in principle, if you take two different open books for the same contact structure, you might get different bourgeois manifolds, and you do in general. But there's a relationship between them. So if I start with two different open books for the same contact manifold, there is a symplectic cobordism between them, which is actually a concordance. So it's a trivial product. Okay, so it's interval times n times T2. Okay, so they're related to each other by this cobordism, and it goes in. There's one in each direction. Okay, so this is you shouldn't think of this as an oriented cobordism. I mean, this is sort of a symmetric condition on the open books. Okay, so this is also something that will pop up in our proof. And so this is we will use about the bourgeois construction. Okay. And then the last sort of ingredient in the proof, and this will be one of the sort of main ingredients, this is H principle of Filiashberg and Murphy. So Yasha and Amy, what they tell you is that if you start now with an almost symplectic cobordism, so a cobordism, smooth cobordism with a non-degenerate two-form omega, which is nice at the boundary, so it's like a symplectization form at the boundary. And if you're in dimension at least 4, and you also have to assume that the boundaries are non-empty. Okay, so this is also important. It doesn't work for a filling or a cap. Okay, so if you start with this data, and if you also suppose that the contact structure at the negative end is over twisted, and if you're in dimension 4, you also need to assume that at the positive end, the contact structure is also over twisted. Then what they tell you is that you can actually homotope this information to an actual Liouville structure on the cobordism. So there exists an exact symplectic form, d lambda, which is actually a Liouville form, which is homotopic to the original one as almost symplectic structures. relative boundary, but in what I'm calling here a conformally relative boundary. It's maybe not a great name, but they cannot on the nose control the contact forms at the boundary, but they allow to multiply by positive functions. Okay, so this is a bit of a sort of footnote in the result, which gave me a few headaches, but it won't be an issue for us. Okay, so but that's a statement, and this will actually be used in our proof. So okay. So then let me state the main auxiliary result in the proof of our main theorem. And this is exactly a stabilization of Borman-Murphy's result. And so this is what I will call a stabilized H principle. So the statement is the following. So you start with an almost symplectic cobordism, the same as Borman-Murphy. And you also need to assume that the boundaries are non-empty. And you just take an area form on T2, mu. And what we do is we stabilize this cobordism, just take the product with T2. And the claim is that, well, we can find an actual symplectic form, little omega, which is first homotopic to the stabilization of the two form through homosymplectic forms, also relative boundary in this conformal sense. There's also a footnote here. I mean, conformally here means we only multiply big omega and not mu, so mu is always fixed in this homotopies. But anyways, and the second condition is that the cohomology class of the symplectic form is lies in the cohomology class induced by the area form mu. Okay? So this is a stabilization version of Borman-Murphy, and this will be the main technical input. But one thing that you should note here, and one thing that should strike you, is that there's no assumption on overtwistedness at the boundary, as opposed to the Borman-Murphy H principle. So I'm not assuming that the contact structures at the boundary are overtwisted in any sense. Okay? And I can do that because I allow myself to multiply by T2. I mean, this is also the key. Okay. So this is basically what the main input is, because the main theorem follows very easily from this result. Okay, so this is how you prove the main theorem from this stabilization of Borman-Murphy H principle. So you just say, okay, start with a formal symplectic manifold, and you take your divisor sigma, which exists by assumption. So it's positive symplectic divisor. The first lemma they have to prove, which is not hard, is say, okay, we're assuming that the two form is symplectic along sigma, but we also want to have a neighborhood in which it is symplectic, which is also symplectically concave. Okay, I want to have some sort of cap around that divisor. And well, it's not hard to achieve because the normal directions are two-dimensional, right? So you just need to correct this two form along those directions, and you can. Okay? And the fact that you get a symplectically concave neighborhood follows from the positivity condition that we impose. Okay? So this is sort of where that positivity is used. Okay, so this is not hard, so you can prove that. And then the theorem follows very easily because you say, okay, first of all, I have this neighborhood in which is symplectic. I take a point away from that neighborhood. I can also homotope omega near that point to make it symplectic. So I can actually find a symplectic Darboux ball near a point. And I just basically split my manifold into three pieces. So there's this symplectic ball, there's an almost symplectic cobordism in the middle, and then there's sort of symplectic neighborhood of the divisor. And so X here is an almost symplectic cobordism from a sphere, which is standard contact structure, to some contact manifold Y. Okay? So if I take the product with T2, of course, I have a symplectic structure on B and on this neighborhood. So I also get an obvious product symplectic structure on the products with T2. But then I cannot get on the nose a symplectic structure on X. But the claim is the one that I claimed before is now I can actually do that after I stabilize. So you just take the product with T2, and the stabilized H principle allows you to conclude that you have a symplectic structure on X times T2. So after stabilization, okay. This is sort of annoying thing that this is only conformal near the boundaries, but in this case, it's not an issue because I can always sort of attach small Corollary neighborhoods which correct for those conformal factors. Okay, so that's sort of how the proof follows from the stabilized H principle. So this is, I mean, the picture is this one. So you have your M manifold M. This is your concave neighborhood. This is a symplectic ball. In the middle, you have this cobordism. And then you have a symplectic form here, symplectic form down here on the ball. You don't necessarily have a symplectic form here next, but you do after you take the product with T2. Okay, so that's sort of the sketch, the pictorial sketch of the proof. Okay, so now everything reduces to try to understand what happens on a cobordism. And so that's what comes next. Okay, so this is how you prove the main auxiliary result. So first of all, we will do the case of a concordance, right? So it all will reduce to a trivial smooth cobordism. So concordance for me is just a smoothly trivial cobordism, just a product interval times the manifold. And there's a nice fact, and this fact sort of basically follows directly from the BEM H principle. So if I take any contact manifold and I look at the over-twisted representative, so the unique over-twisted contact structure, which is homotopic to it, I can always find an almost symplectic cobordism between them, okay, which is also concordance, so it's just a product. You can convince yourself because basically the data of a concordance with an almost symplectic structure is equivalent to having a path of almost contact forms, almost contact structures between these two contact structures. Okay, so at each slice. Okay, so this basically follows directly from the H principle of Borman and Murphy. So okay, now we have this concordance. And the theorem that we prove, and this is the essence of the stabilized H principle, is that when you take the product with the two on this particular cobordism, then you can sort of solve the stabilized H principle. You can find sort of your symplectic form that you're looking for. Okay, so this is where all the complication is. Okay, so the main result follows from the version from concordances in a fairly straightforward way, again, and similarly as before. I mean, this is a picture. So you start with some cobordism W, and then it has some contact structures at the boundary. And what I can do is, up to homotopy of the almost symplectic form, I can sort of arrange the existence of the scalar neighborhoods near the boundary on which the contact structure now becomes over-twisted. So I can sort of plug in this particular concordances near the boundary. And you should observe that I can do it in both directions, right? So I can make an over-twisted contact structure here near the boundary and another one here. So now I've found a subcobordism, which is almost symplectic, but now has over-twisted ends. Okay. And so Borman-Murphy applies here. So in particular, after I take the product, I also get a symplectic structure. So now all the complication has been pushed to this color neighborhoods. Okay. So this is where our result comes in. So we prove that when you take the product with 2 on this trivial concordances, then we can actually sort of get rid of the obstruction that we had before. Okay, so that's sort of, in a nutshell, how the proof goes. So that's the strategy here. Okay, so now we reduce everything to proving this result for the case of a concordance. And now you should remember what I said about the bourgeois manifolds, that this monodromy inversion doesn't change the bourgeois construction, because what I will end up doing is, on the boundaries of this cobordism, I will take the product with T2 and then need to find suitable open books. And then I will basically invert the monodromies. Okay? So with that in mind, this motivates this next theorem, which we're calling the monodromy inversion theorem for obvious reasons. And it says the following. So you start with any contact manifold, and you take the unique over-twisted contact structure homotopic to it, the over-twisted representative. And the claim is that we can find open books for this contact manifold, which support respectively xi and its over-twisted representative, such that if I invert the monodromy in this open books, I get open books for the original manifold with opposite orientation. But these open books support 2 auxiliary contact structures, which I'm denoting psi inverted and psi over-twisted also inverted. These inverted contact structures are also over-twisted, but they're actually isomorphic to each other. So in other words, I start with whatever contact manifold, and I say I find 2 open books, and such that if I invert their monodromies, I get over-twisted contact structures, and they're actually sort of the same contact structure up to isomorphs. Okay. So I think, I mean, this result may bear some independent interest on its own, so I'm stating it as it is. So maybe let me give a sketch of how to prove this, because this is also sort of one of the key parts of the result. So I'll give a sketch now of this monodromy inversion theorem. So this is how it works. So you want to do it for any manifold, but there's a very simple connected sum argument that allows you to reduce it to the sphere. Okay. If I have it on the sphere, if I have these 2 open books, and I take an arbitrary manifold, I can assume that the over-twisted representative is just a connected sum with a negative stabilization. And then I can basically sort of put the open books on the original manifold by a connected sum formula. Okay, so everything reduces to the case of the sphere. But now the advantage is that in the case of the sphere, we have a classification for almost contact structures. So this goes back to computations done by Harris in the 60s. So Harris tells us that, first of all, this is a group, right? The set of homocontact structures on the sphere is a group. So the group operation is just taking connected sums. But it's actually this homotopy group here is sort of pi to n minus 1 of this homogeneous space, okay? SO2n divided by UN. And there are 4 different cases. So there are 4 different cases according to the value of n modulo 4. Okay? And half of them, you have a finite group, which is n equals 1 or 3 mod 4. And then the other cases have infinite groups, okay, z and z plus z2. So this gives us two different cases. Case 1, where n is odd, corresponds to finite group. Case 2 and even correspond to infinite group. Okay? So roughly speaking, sort of, well, not roughly speaking, sort of the existence result of Borman-Murphy tells you that this group parameterizes all of the over-twisted contact structures on the sphere. Okay? So if you want to ensure that 2 over-twisted contact structures are the same, you just need to match the corresponding elements in this group. So that's the idea. The easy case is case 1, where you have a finite group, because you can just use the order of the group. The difficult case is the infinite group case, which took us a bit of work. So case 1 is fairly straightforward. This is basically stabilization tricks. You take the order of this group, which is finite by assumption. And first of all, the standard contact structure on the sphere is supported by an open book whose page is T star is n minus 1. And the monodromy is the dense Heidelberg twist. Okay, so it's symplectomorphism of this sort of this manifold here. Okay, so it's basically the positive stabilization of the trivial open book on the sphere. And then the second is we just take an arbitrary open book supporting the over-twisted version of this standard contact structure. So they both represent the 0 element in the group of almost contact structures. Okay, so since the standard contact structure is 0 in this group, I can just take any number of self-connected sums and it won't change that, okay? Because I'm just multiplying 0 by k. So I just take a bunch of self-connected sums and I have this sort of open book decomposition, I have this sort of connected sum formula. We just need to take the boundary connect sum of the corresponding pages and monodromies. Okay? So I have, first of all, this equation here. And then the over-twisted version also represents 0 by assumption. So I can also take a bunch of self-connected sums where I take exactly k of them, where k is the order of the group. Okay? So this is also ensuring that I still get 0 every single time. Sort of remember that stabilizing with the standard contact structure doesn't change the isomorphism class, but because psi is over twisted, I can ensure that I get sort of this equality here. And I also have the sort of connected sum formula. Okay, so I found 2 open books for the standard contact structure and its over twisted version. But now if I invert the monodromy here, you have to look at sort of these expressions here. I pick up a negative stabilization in each of them. Okay, k is at least 1. But negative stabilizations are precisely over-twisted contact structures by a result of Casals, Murphy, and Presas. Okay, so they're over-twisted. And they also represent 0. So they represent the same element in the group. I'm done. Okay, so that's I found 2 open books for these 2 contact structures such that I invert the monodromies. I get 2 over-twisted contact structures, and they're the same. They have the same sort of formal class. Okay, so they're isomorphic because they're over-twisted. Okay, so that's how this works in case 1. Case 2 is the hard one. This is the infinite group situation. It's a similar argument, so it's a very similar trick. You just do a bunch of stabilizations, but matching the elements in this group is a bit trickier because you need to know something about negative stabilization on the sphere. So if you take the sphere and you look at the negative stabilized open book, so the inverse of the Heidelberg twist, you have some corresponding element in the group, but we don't know exactly what that element was. What we can show is that in this case, for even n, it actually has infinite order, okay, in this group. So this is a lemma that we had to show. I mean, we couldn't find anywhere in the literature anyone saying anything about this particular element. So we just had to prove something ourselves, which was enough for our purposes. But maybe a remark. So if you're on S3, this negative stabilization is well known to correspond to -1, which is the corresponding group. In this case, is just the integers. And this guy is a generator of that group, in particular, has infinite order. But as far as I could tell, for other ends, the exact element in this group seems unknown. I mean, at least I couldn't find it. So if you know what this element in this group is for negative stabilization, we'll be very happy to learn that. Maybe it's something that one can give to a PhD student, to a smart one. And that might be something that I actually do in the future. But anyways, so this result will be enough for our purposes. Basically, it's just throwing out a very few actually two cases which are bad for the argument. So either 0 or in the case where it's z plus z2, 0, 1. Okay, so this is the only element which doesn't have infinite order in this group. Okay, so in particular, this shows for even n, this negative stabilization is not in the same class as the standard contact structure. It's non-zero. All right, so this is something I have to prove, and then this gives you the infinite group case, and you're happy. Okay, that's the end of the sketch. All right, so now we have this inverted open books. Now let's go back to the proof of concordance. We have this trivial product m times the interval. It's an almost symplectic concordance between a contact structure and its over-twisted version. Now you take these two special open books that we constructed. They're inverted monodromies, and they support auxiliary isomorphic over-twisted contact structures. But now I achieved the contact structures are the same. So I can appeal to the previous bourgeois manifolds, its properties of the bourgeois manifolds. So I have two different open books supporting the same contact structure. So I can find a concordance between them. Okay, so because they're isomorphic, there's a symplectic concordance of this form between the corresponding bourgeois manifolds. And here, I mean, the orientations are all swapped in both the factors, in n and in T2. Okay, so I take not mu, but minus mu in the T2 factor. So this is part of the trick. Okay, the cohomology class of the symplectic form is minus the cohomology class of mu. Okay? But then this diffeomorphisms of this inverted monodromy diffeomorphisms will allow me to flip back the orientation. So that's also the trick. Okay, so this is what you should recall. Now, if I invert the monodromy, I didn't change the bourgeois contact structures. So I have this concordance on this swapped orientation, or what the orientations are swapped. And I just basically observe that these diffeomorphisms are actually both isotopic to each other, because they're isotopic to just this diffeomorphism, which takes just the identity on the first factor, and it just basically swaps the orientation on the second factor on T2. So in particular, they extend to a concordance. Okay? So they're isotopic to each other. I can find a concordance which at the bottom, I get one of the diffeomorphisms, and at the top, I get the other one. Okay? So I have a one-parameter family of diffeomorphisms between them. We can actually write down such a map F explicitly. So what this map F does is flips back the orientation on the two factors. And then we just basically pull back the symplectic form that we found in the previous lemma to this concordance. And basically, we're nearly there. Now we have a symplectic structure here. We just need to control the homotopy class, the cohomology class, and so on. And that's the last part of the proof. So the end of the proof is, okay, as I told you, this omega, as I constructed it, this omega may not have the same boundary conditions as the stabilization, but there's a lemma of Massot, Niederkruger, and Chris Wendell that tell you that you can correct that. Okay, so these are weak boundary conditions. So the contact structures at the boundary are weakly dominated, and the cohomology class is the correct one, so I just correct that. So now I achieve that the boundary conditions are the same, and then I need to control the homotopy class. And so what I do is, well, first I homotope my symplectic form to be split. So it's of the form omega tilde plus mu, where omega tilde has no T2 terms. Okay, so I homotope it to be of this form through almost symplectic forms. But now this omega tilde, because it's an almost symplectic structure on a concordance, it's the same thing as a loop of almost contact forms based at the over-twisted representative. But now I can use Bem's parametric version of the H principle that allows me to correct also. Up to adding another concordance which corrects for this difference, I can control the homotopy class. Okay? And then the last observation is that the homology class the symplectic forms lies in the correct cohomology class in the general statement, basically by assumption. Because on this concordance, the cohomology class is exactly the one given by the area form, and I'm assuming that the divisor is also compatible with the cohomology class theta that I fixed originally. Okay, so that basically allows me to conclude that the cohomology class is the right one. Okay. And yeah, so that's it's a short talk, but that's the end of the talk. So thank you very much.
Okay, let's thank Agustin for this talk. Wonderful. Any questions?
I mean, I don't know very much about, I mean, I've been thinking about symplectic geometry in dimension 4, so I don't know much about it in higher dimensions, but it seems that the structures you're constructing are they're the analog of over-twisted contact forms, right? They're over-twisted symplectic forms in some sense. I mean, you'd imagine all the Gromov-Witten invariants would vanish, et cetera, et cetera. Is there any formulation of that? I mean, is there anything you look for to say what that would be?
That's a good question. It's a great question. I don't know. I mean, potentially what you could try to do, I mean, this is existence, right? You might try to prove some sort of uniqueness statement to start with. If you have two such sort of symplectic structures on the stabilizations, maybe you can show that they're, I don't know, isotopic to each other. I don't know.
Sorry, but if I understand correctly, the point is that even if you start with an over-twisted contact structure, when you do this construction, you get something tight. So by the time you stabilize, you've somehow gone back into the rigid world, even if you started with an over-twisted contact structure, which does seem quite mysterious.
Yeah. So I'm not sure how to answer that. I mean, yeah, it's a good question. It might be that every sort of holomorphic curve invariant vanishes for this particular symplectic forms. I have no idea.
Right. I mean, I just don't have any understanding. You could look at a Donaldson decomposition, presumably. I mean, look at a Donaldson divisor in it, and
yeah, exactly. So I mean,
see what the complement would look like.
One question that I was thinking about, I mean, Fran suggested to think about this actually. So it might be the case that, as you say, you have a symplectic structure now, so you also can use Donaldson, so you have divisors, right? It might also be the case that if you start with a symplectic structure on this product, you might also get a divisor on the original one. So that this assumption that we're making is sort of the best one in some sense. And then you might start thinking exactly along the lines that you suggest. But I don't know. I mean, it's sort of, yeah, it's a question for future work.
Yeah, no, it's very interesting talk.
Okay. I mean, in high dimensions, of course, ensuring the existence of a divisor, it seems a bit sort of difficult. In dimension 4, it's not so much. Basically, just the results that I was mentioning, results of Bohr and so on. I mean, I also don't know in general if you start with an almost symplectic manifold whether it admits symplectic divisors. Dimension 4, that might be true. We cannot prove that, but I mean, I think it's also some question to think about.
Right.
It might also be true that if you start stabilizing like an arbitrary number of times, then you eventually get a divisor. If you start with arbitrary sort of almost symplectic manifold.
Yeah, I mean, just for contact manifolds, the contact structures you can surely construct are almost always over twisted, right? I mean, being tight is very, very special. And so it would just seem to me that because you're going through over, I mean, I don't understand the over twisted things, but since you're using that very much as a part of your element and what you're constructing, it would seem to me that these would have to be sort of the equivalent of over twisted in some sense. But
yeah,
it would be very interesting to know that. I don't know. It's really good.
Yeah, it would be interesting to think about the right formulation of that would be.
Mm-hmm. Yeah, exactly.
So maybe I can ask again, just to try and understand the structure. No, so okay, so yeah, symplectic cobordisms are flexible if the bottom is over twisted, so that's fine. So you construct it, but then the problem is you want to go back, so you want to kind of invert the end and go back to the over twisted, and so for that you can't do it. But once you stabilize with T2 because of this monodromy inversion, you can somehow do it, and then you close it up. And
that's a claim. Yeah, exactly.
that's the claim. Okay.
So it's sort of basically Murphy, like if you just apply this sort of construction, then basically you cannot match the ends, right? Sort of, it's not what we're doing is sort of pushing all the difficulty to the boundary, and then sort of fixing it up after taking the product. I mean, sort of intuitively, I think what's going on.
But yeah, I mean, I was also wondering about what Dusa was saying. But the thing is, like, I already find surprising that if you start with an over-twisted contact structure, then you do this bourgeois construction. I mean, in an open book, and you do this bourgeois construction, then you get a structure on the product with T2 that is tight. Like that to me is already kind of mind blowing.
Yeah, it's crazy.
Like I would expect whatever you do with an over-twisted, it's just gonna be over-twisted. I mean, I don't know. I don't care if you do this, if you do that. Like, how could you suddenly get something tight?
Yeah, I mean,
but I haven't read that that paper in dimension 5 in the recent paper, but I'd like to understand. Is there a way to explain, like, simply why it's tight?
I can tell you how we prove it, but I'm not sure that's going to be very enlightening. I mean, the idea in dimension 5, right, which is very different from the current proofs that Zhengyi and Russell are claiming, is first of all, the first inkling that this phenomenon might happen is this monodromy inversion, right? You can do the following sort of mental exercise. You can say, okay, I start with a positive stabilization of a standard contact structure on the sphere, and I do this bourgeois, right? But I can also do the negative stabilization and do the bourgeois. But now the positive stabilization is fillable. So it's not hard to show that if you start with something fillable, then if you do the bourgeois, you get something weakly fillable. So in particular, tight. Okay, so, but now you do the inverted version, okay? So it's not weakly fillable, it's actually over-twisted. But when you do the bourgeois, it's basically isomorphic to the other one, right? So it's also tight, right? So that's the first sort of inkling that this phenomenon happens, right? And the way to prove it is, well, in our case, we really use the mapping class group of the surface. So the surface is the page of the open book. What we show is that, first of all, there's if you take two monodromies, right? This is sort of stabilized version of this construction of Russell and also Klukas. So there's a pair of pans cobordism from the bourgeois corresponding to the same page with one monodromy and the other monodromy to their composition. Okay, so you have sort of this pair of pans thing, and then basically you also show that you can if you take any monodromy, you can write it as the composition of two monodromies, at least for most surfaces, such that if you separate them in two, then each of them are actually hypertight. Okay? So then you have this pair of pans thing. You try to run the Hofer argument, right? You sort of say it's actually over twisted, and then you have this sort of over twisted object, and then you run the Bishop family, but the negative ends are hypertight, so you run into a problem. Okay, so that's sort of in a nutshell what we did. I'm not sure if that helps. What Russell and Zhengyi seem to be doing is they go to a cover, so they have this bourgeois thing. Now you cut one of the circles, so you unravel it. Now you have S1 times R times the original manifold M, but now you have this convex decomposition of this bourgeois structure. And Russell has been doing a lot of work on trying to understand homomorphic curves in general, like neighborhoods of convex hypersurfaces. So in particular, he has this sort of bilinearized version of contact homology. So when each sort of piece in the convex decomposition gives you linearization. And then he has this criterion which generalizes Giroux's criterion to higher dimensions. And he can show that in many cases, contact homology is non-zero. You basically need to understand homomorphic curves and intersection theory and so on. And he uses Cornishi structures, right? Okay, so there's multiple covers. You have to pick whatever Poisson you want in order to deal with multiple covers, right? And then they do that and they show contact homology is non-zero. But then if you have that on a cover, you also conclude that on the original manifold, right? So I think that's their strategy. It's very different. And it bypasses the fact that we use the mapping class group. They don't have to. So I don't know. We have now we have two different proofs in dimension 5. Let's and then
Great, thanks. Very interesting. Yeah.
Okay, maybe we should kind of start. First, thank Agustin for a wonderful talk.